So next up is Anders Willen from VTT. Anders is going to be talking to us about time, which is always an interesting subject. But if you're looking at getting involved in 5G, it's suddenly going to become a lot more critical for your day-to-day operations if you want the network to work. So over to you, Anders.
Thanks. So hi, my name is Anders Wallin. I work as a research scientist at VTT Mikes, the National Metrology Institute. If you're in general interested about science and metrology, you should hold on to your hats on Monday, because on Monday we changed to use the new SI systems. 4 of the SI base units are redefined, so you have to tell your kids how the kilogram is nowadays defined by fixing the Planck constant, not the kilogram in the stored somewhere in Paris. So anyway, we won't change the definition of the second on Monday, so that still stays.
That's Tuesday.
That will stay the same. Yeah, if you use inches, you're fine. So anyway, on time and frequency, we see an increased demand for accurate time in several different parts of society. So I'll highlight some of those. How we do timekeeping in the national labs. Finland is a small country, so we only have one UTC lab. But for example, in Germany, they have, I think, 3 or 4. Deutsche Telekom, the space agency, and so on, thinks that timekeeping is so important, so they have their own UTC labs, but we have one. And then the main part is time transfer, where we've been interested in the PTP protocol, which has been called White Rabbit for a long time, but now is going to be included in the next PTP revision as the high accuracy profile. We've been using that for a number of years now, and we have results on small and large networks. And then recently we did a research project on distributed timekeeping, which probably is the way of the future. So the needs for accurate time in telecom have been following these ITU standards, where basically the oldest one is only a requirement on frequency. And this one you fulfill by just buying a cesium clock and turning it on. That's no problem. But these recent ones, really I think the message is that they approach the level of what most national labs do. So it's really not trivial to independently keep time to 100 or 30 nanoseconds, which these primary reference time clock standards talk about. In particular, this most accurate and newest one. This, of course, applies to the time source, which you have somewhere in your server room, or perhaps few of them across the country. Then another issue is what do you require at the far user end of your system. Smart grids is another area where everything is moving to digital. So instead of measuring analog 3-phase voltage, 3-phase current, everything is digitized, and then you share the digital information. Now if that phase of the 50 Hertz waveform is incorrect, then you get into trouble. And so if you do a calculation of that kind of phase vector of your 50 Hertz AC, you want 1% vector error on the in total. Then you also end up at a roughly 1 microsecond timing requirement for smart grids. And then finally, coming more from a sort of regulation point of view and with perhaps less strict requirements, we have e-commerce, in particular this MiFID II directive, which says that if you are quite close to a trading venue and you do trades every millisecond or every 5 milliseconds, something like that, which is quite common nowadays, then you should timestamp all your trades with 1 microsecond resolution and 100 microsecond accuracy. So this is definitely not something you can do with traditional NTP over your packet switched normal internet. And similarly for timestamping of digital documents. So that were some of the needs. How do we maintain time then worldwide? Well, we do it with atomic clocks. So they look something like that. And you place them in a stable environment and they will be pretty good frequency standards. But a commercial clock like that won't keep within that, say, 30 nanosecond window, which is your ITU specification, for very long. So you need a kind of feedback system where everyone reports how their clocks run. The international body computes a correct paper timescale, which nobody really has, but it's a sort of theoretical correct timescale, and then feeds back those corrections to all of the labs. So in particular, something called an active hydrogen maser, which costs around maybe 200,000, is a quite good frequency standard, but we see that the phase measurement there is kind of like a parabola, so that means that the frequency is more or less linearly drifting. And so within these 100 days, maybe we stay within that 30 nanosecond requirement. But the point here is that you can't really buy clocks that are accurate by themselves. What we rely on is the predictability, that when we keep these in a stable environment, they are predictable, and then we have ways of correcting how they behave. And so this is then the feedback loop with a 1 month time constant. Every month we get this report from the international BIPM body, and our lab is one line here, and quite randomly I've picked a month where we did fairly okay. So Finnish timescale was within 1 nanosecond of the theoretical UTC timescale that is computed by the BIPM. So then if we manage to do this timekeeping with the atomic clocks, then we go on to do time transfer in the network with different techniques. And these divide quite nicely into two different accuracy scales. So the traditional NTP, where you have switches and delays, queues, whatever, it goes down to maybe single milliseconds in good environments. But then when you do hardware time stamping and keep track of delays within the network with traditional PTP, you get down to 2 microseconds. And the one which we've been interested in is now this high accuracy profile of PTP, where we have hardware time stamping combined with synchronous Ethernet between the devices. And so you see here also a comparison that if you make the investment to have some kind of PRTC or ePRTC level of clock in your lab, then it probably makes sense to use the same level of time transfer technique also to move that to other places. And all of them work by exchanging timestamps in roughly the same way. So if you have a master clock somewhere and it wants to transfer time to a slave somewhere else, and time goes forward in that direction, we record these 4 timestamps of this packet exchanged, and if you from this gray one subtract the green one, then you end up with the red ones, which is the round trip delay. And then you make this bold assumption that perhaps the one-way delay is half of the round trip delay. And that's always the crucial assumption in these schemes. And so in NTP you do all of this in software. In PTP you do it in hardware. And in the high accuracy profile you do hardware timestamping plus this synchronous Ethernet phase comparison. And you also worry about, is your path really asymmetric? So is this really true? In practice, we see anywhere from 3 to 100 parts per million error in that 1/2 constant there. This is a little bit more technical on how White Rabbit or the high accuracy profile achieves these kinds of accuracies. So the scheme is there, and the timestamps that need corrections are the ones when you receive something, because if you send something, you can choose to do it on a rising edge of your own clock, and you know exactly when it went out. But these T2 and T4 are enhanced by this kind of accurate phase measurement, which is similar to what you have in your mechanical calipers to read out the tenths of the reading. So we've been piloting this on a number of links, and this one is in the FUNET network to our Kajaani site, and was one of the first demonstrations of long-distance White Rabbit, where we go in the conventional DVDM system. So we have two fibers and amplifiers in between, but the path is completely optical from Grandmaster to the slave node, and we did a comparison against the GPS receiver, and we found that the link is at least within 2 nanoseconds over a long 100-day period. This 2-fiber architecture does introduce constant asymmetries, which you have to take into account. More recently, we have piloted in this kind of Matine project funded by the Ministry of Defense, this kind of clock network idea, where we know that we have sites with different clocks, either at our sites or our partner sites. We've connected them all with this White Rabbit technology and measured them all against each other, and by this scheme able to maintain time at not only our lab but also at customer or partner sites. So currently we have maybe 10 nodes and 14 clocks roughly in this experimental research network. So one way of characterizing this network is this loop, because if you go, let's say, this way to M2 and the other way to M2, then the difference between those two should be 0. So that's what we call a where should I point this? Closure error. So around this kind of loop, the good and bad news are that the bad news is that there is typically large offsets. If these links are conventional dual fiber things, not bidirectional, but 2 fibers, you can't really control how much asymmetry you introduce, and we find several microseconds for several 100-kilometer links. So we have a large offset of 5 microseconds in this closure error, but the good news is that if you don't go and break your fiber and have to repair it or do some other funny things on the optical path, then this offset is very, very stable. So we find something around half a nanoseconds over 200 days, which is very good. So that brings me to the conclusions. So really these PRTC and ePRTC requirements are sort of approaching the level that national labs currently try to do. So if you have those in operational conditions, you are in for a challenge, I would predict. Satellite signals are of course widely used, but the question is then how much critical infrastructure do we want to put on GPS or GNSS or Galileo or something like that. Every time our neighbors in the east have a military operation, the GPS may or may not work depending on where you happen to be. So we have good experiences with this White Rabbit and high accuracy protocol. The trick really is managing these asymmetries that you have in the network. So the 2-fiber solution, which is the common one, always introduces asymmetries, and then with bidirectional links you can try to limit that only to chromatic dispersion between the TX and RX wavelengths. And so we now operate around 1,700 kilometers of tying links to mostly research institutes and initial pilot users who have been interested in precise time. But but there's an increasing discussion now with key players that do we need a national and more reliable timing network. We would really place atomic clocks in several different locations and provide robust timekeeping. And so if you're interested in this topic, I've listed a few references. We had the Martinet project. The GSA is the EU agency responsible for Galileo. They are very keen on Europe starting to use Galileo. And then there are various White Rabbit resources. That's it. Thank you.
Thank you. Are you going to be here this evening for sauna?
Yes, for some time, yeah.
Super. Can we do questions then, and then we can maybe try and catch up a little, because we're running 40 minutes behind. So next up is Vic.